What if I told you that the screen you're looking at right now, the lights in your room, your phone, it's all powered by a single, totally invisible partnership? Well, today we're going to pull back the curtain on the two fundamental forces that run our modern world: electricity and magnetism.
I mean, just take a second and think about the screen you're watching this on. It doesn't matter if it's a phone, a laptop, or a TV. It works because of a few core principles. And these aren't just some abstract ideas in a textbook. They're invisible forces that are literally at play right now, all around you.
So here's the game plan for our journey today. We're going to start super small, in the atom-sized world of electric charge. Then we'll see how those charges create fields and get them moving in circuits. From there, we'll bring in magnetism, its partner in crime, and finish up with the one concept that literally powers our entire planet: induction.
First stop, the world of charge. And you've got to get this part, because every single thing we're going to cover today, from a tiny little spark to the entire power grid, it's all built on this one fundamental idea.
You see, a charged particle doesn't just sit there. It radiates this invisible field of influence all around itself. We call it an electric field. The best way to picture it is kind of like a spider's web. Any other charge that wanders into this space is going to feel a force, either a push or a pull, from the one sitting at the center.
So, how strong is that push or pull? Well, this super simple equation tells us everything we need to know. The field strength, that's E, is just the amount of force, F, that's felt, divided by the amount of charge, Q, you're testing with. So in other words, it tells you exactly how much of a nudge any charge will feel if you place it at that specific spot in the field.
Okay, so we know these fields exert a force, but they do something else that is absolutely crucial. They store energy. And understanding this stored energy, or potential, is really the key to making electricity do useful work for us.
Now, it is so important to get the difference between these two things. The electric field is what we call a vector. That just means it has both a strength and a direction. It's like a signpost that points and says, go this way with this much force. But electric potential, that's a scalar. It's just a number. Think of it like the elevation on a map. It tells you how much energy is stored at that point, but not which way the hill is sloping.
So whenever you hear somebody talk about volts, this is all they're talking about. It's our unit for electric potential. 1 volt is just 1 joule of energy packed into every single coulomb of charge. It's pure, stored-up energy, just waiting to be unleashed.
All right, so we've got our heads around static charges and all the energy they're holding. Now, let's make a move. This is where we get into circuits, which are basically just the highways we build to guide the flow of electricity.
And listen, if you only remember one thing about circuits, make it this: Ohm's law. It is a beautifully simple relationship. Voltage equals current times resistance. This one single equation is the foundation for almost all of modern electronics. It's that important.
You know, the absolute best way to understand this is with the classic water pipe analogy. It just makes perfect sense. Voltage, or V, that's like the water pressure pushing everything along. Current, or I, that's the flow rate, how much water is actually moving through the pipe. And resistance, R, well, that's just the width of the pipe. A skinny pipe creates high resistance, right? While a big, wide one lets the water flow super easily. It's a perfect mental image for how these three things connect.
And resistance isn't just some random number. It's based on physical properties of the material. Just look at this chart here. A long, skinny wire, like you see in that first bar, has a pretty high resistance. But a thicker wire, like in the third bar, gives the current a wider path to travel, so its resistance drops. It's simple. More length means more resistance, more width means less.
Now, how you actually arrange the components in a circuit, those pipes, has a huge impact on how the whole system behaves. So let's look at the two main ways you can build a circuit.
So in a series circuit, it's pretty straightforward. There's only one road, so every resistor you add just adds to the total traffic jam. Simple enough. But in a parallel circuit, here you're adding new roads, and this is where things get a little weird. The math is a bit different, and it leads to a result that might just break your brain a little at first.
So here's the key takeaway. Get this, when you add another resistor in a parallel setup, you're not actually increasing the total resistance. Common sense might tell you that's what happens, but you're actually doing the complete opposite. It actually decreases the total resistance. But why? Well, think about it. You've just opened up a whole new lane on the highway. Even if that new lane is a bit slow and bumpy, it's still another option for the traffic to take, and that eases the overall congestion. More paths mean less total opposition to the flow. Pretty cool, right?
Okay, so we've been talking a lot about electricity, but here's the plot twist. It doesn't travel alone. It has an inseparable partner, a twin force, magnetism. It turns out anytime you have a moving electric charge, you automatically get a magnetic field. They're a package deal.
And the relationship between them is direct and totally predictable. First, you start a current flowing through a wire. Then, a magnetic field just forms automatically in these nice little loops around it. If you crank up that current, the field gets stronger. And just like you'd guess, as you move farther away from the wire, that field gets weaker.
And now for the grand finale. This is where everything we've talked about comes together. We've seen how electricity can create magnetism, but can it work the other way around? Can magnetism create electricity? The answer is a huge, resounding yes. And this one principle is arguably the single most important discovery for our entire technological society. This is electromagnetic induction. We have the brilliant Michael Faraday to thank for this one. The principle is this. If you simply change a magnetic field near a wire, you will induce a voltage and, because of that, a current in that wire. You don't even have to touch it. The changing field itself creates the electricity out of thin air. It's like magic.
Of course, nature always seeks balance. Lenz's law basically tells us that the new current you just created will generate its own magnetic field that always pushes back against the original change. It's kind of like nature's law of inertia for electromagnetism. It always resists being changed.
And I am not exaggerating when I say this one single idea is the engine of our modern world. It's how those massive generators and power plants create all of our electricity. It's how transformers step that power up and down to move it across the country. It's the principle that spins every single electric motor, and it's even what's behind the wireless charger for your phone. It all comes down to induction.
So, there you have it. From a single electron all the way to the entire global power grid, it is all so elegantly connected. And what's truly mind-blowing is that these rules were discovered over 150 years ago, with tools that were way simpler than what we have today. It just leaves us with this one thrilling question. What's the next fundamental force we're on the verge of discovering, and how is it going to completely change our world all over again?